Cool, all right. Hey, thank you all for coming. Appreciate everyone coming out to listen about Kafka with Danica. A couple of neat, cool things about Danica. She's a crazy plant lady, or is a crazy plant lady?
I am still, yeah.
She was younger, she collected sugar packets.
You can talk to me about sugar packets any day.
Figure all that out. So we're really super excited to have her. It's a busy week for us. There's a lot of conferences going on. The Ignite Summit's Thursday. Everyone going? Yes? If you're not going, go, please. I'm co-chair of that, so I just love the whole kind of data community and the tech community here at Richmond. So, what was that again? RVA Tech Data and AI Summit? Oh. It's Thursday. You're not going?
I don't know where these things are posted, but they're never working in museum.
Well, there's still time.
There's still time. There's still tickets available. We broke pre-2018 numbers on ticket sales.
That's incredible. That's a big deal.
So, Danica, appreciate you guys here.
Yeah.
Pizza and some of the beverages are on Confluent, so hats off. Thank you.
Ooh, thanks, Confluent.
I appreciate y'all. Give your attention to Danica. She'll take questions more likely after.
Probably, unless you have like a burning question.
She says she's got about 2 hours of PowerPoints.
Yeah, I could go 3 if you want.
So big round of applause for us.
Well, thanks for coming out tonight. I'm really excited to be here, so I hope you're just as excited to be here. If you can't tell already, I love talking about Kafka. I'm not usually this enthusiastic, but it's really only when I talk about Kafka. Apache Kafka, that is. So, how many of you know about Kafka already? You've used it. Okay, we're pretty good. All right, great. So since you're all familiar with Kafka, this is great, because tonight we're going to learn how to get data into Kafka. How many of you know how to do that already? Wait, nobody. That one person. Okay, so wait, have you used Kafka? Oh, we're all just consumers. Well, okay, anyway. Well, this is still going to be very, very useful, because Kafka is a beautiful black box. Or that's how I love to think about it most of the time. If you're building applications on Kafka, you throw the data in, it's somehow magically stored there, and then when you need to get it out, perfect, it's there for you. And so yeah, I am 100% guilty of treating Kafka like that black box. Because 95% of the time, it works. The black box does what it's supposed to do. You put the data in, and later you get it out. Cool. But what about the other 5% of the time? When, I don't know, you tried to put data in and it didn't really do that thing, that one thing that it said it was going to do for you, right? That's really frustrating, because it's like, Kafka, you had one job, literally one job. And so I have been in that situation many, many times where I'm just so unbelievably frustrated with Kafka. And so I would like to help us not be in that situation ever again. And so yeah, the purpose of this talk is to go back to the basics. We are going to see how you get data into Kafka so that the next time it doesn't work like you expect it to work, you at least know where to start, right? What metrics to look at, which configurations you can start to tune to make it do the thing that you need it to do, right? And so yeah, so let's get started. And we're going to put some data in Kafka. And so if you couldn't tell by the title of the talk, a Kafka producer's request, or there and back again, this is going to be Hobbit themed. So bear with me if you're not a fan of the Hobbits or the Hobbit or Lord of the Rings. But I will try to make it as accessible as possible regardless. So we're going to start off with a schema because we are reasonable humans and we want to use one. So really simple schema, we're going to keep track of the whereabouts of hobbits because they like to go places sometimes. So the name of the hobbit, their current location, and then what they're currently doing. They don't do a lot, so that was easy to keep track of. So we've got the schema, and then we're going to create a corresponding topic that we want to put that data into. Hobbit updates seems like a good name for that topic. And we're going to get into all of these configurations at some point in this talk, but I want to put those up there just so they're in the back of your mind. The number of partitions of this topic, its replication factor, min-in-sync replicas, and the cleanup policy, how we get rid of old data. All right, so we have our schema, we have our topic. Cool. Now we can write a producer in whatever language we want. And I am going to purposefully do some hand waving here because there are so many different clients that you could write, so many different languages you can use to write a producer in Kafka. And there are some fun little nuances to each of them. And I'm going to be upfront with you and say I have not used every Kafka client out there. And so I'm going to try to do my best and call out where there are differences between the clients, just so that you know. But we're going to use the generic producer client right now. So we have a producer. We're going to build up some sort of object, right, adhering to that schema. And so, okay, we've got our Hobbit. We're going to talk about Bilbo right now. He's in bag end, and he's eating because what meal is it? Supper, okay? And I also am going to make the key the same as my Hobbit name. This will come up later, but again, sort of a best practice if I want to look at just what Bilbo has been doing later on. And so we build up this object, we have our producer, and we're going to call producer.send. So it's in Kafka, yeah? Yeah, kind of, maybe, a little bit. I mean, sure. Not always, but generally. For all intents and purposes, when you call producer.send, that data is on its way. Something might get in its way while it's on its way, but generally the data is going to make it into Kafka. But how it gets to Kafka at this point and how long it takes, it's a journey, right? And the reason you don't know about how much of this journey it is, how much of a journey it is because, yeah, it has been abstracted away from you in that beautiful black box, like it should be. Cool. But today we're going to blow that up. We're going to go in and see exactly what happens in this journey of epic proportions. Every single stage that we have to go to in order to take your data from the producer client and make it onto disk and back again. Hence the title of the talk and why it's Hobbit themed. All right, so buckle up. Yeah, so we're going to go through all of these stages. This happens every time you make a request to store data into Kafka. All right, it looks like a lot, and it is a lot. All right, so it's kind of a wonder that it works. I think it's great. So we are going to get into all of these. But before we can even get onto the broker, because I know that this looks really intense over here, right? There's many boxes on this side. There's only one over here. But we have to start over here, and there's a lot that goes on the producer side of things, which kind of makes sense, because hobbits are stubborn, right? They don't like to leave the comforts of their home. So we really have to prepare them to embark on a journey. So we're going to start in Hobbiton bag end with our data on the producer, okay? So we started with that event, all right? We had Bilbo at home eating, and we called producer.send. So the producer does a lot of heavy lifting before we can actually get to the point where we can make a request to store this data on our broker. The first step of the process is to translate this nice little object that we've built up into bytes, because the brokers only speak in bytes. They want to store raw bytes. But I want to look at pretty objects. Okay, great. So we have to serialize our data. An important part of this talk is that I do want to call out all the configurations, or most of the important configurations at each of these stages. So here, at this point for serialization, you can either serialize the key or the value. You can also connect to a schema registry at this point as well. Okay. Now, the next thing, okay, we have our raw bytes. The next thing we need to do is figure out where we're actually storing this data. Okay, we know what topic we want to send it to, right? But Kafka topics are broken up into partitions. So we need to know where that which partition we're actually storing that message in. And there are a few configurations that affect how this is done. The biggest one is the partitioner class configuration. This defines at a high level how we're going to partition our data. And you have a couple options. So if this isn't set, we're going to use the default partitioning strategy. So this says that if there's no partition specified as part of your producer.send call, your message, then we are going to choose a partition based on the hash of the key. So it's kind of important that you have that key in there, right? So that we are sending it out to a partition and consistently sending it to that partition so that all of our Bilbo events are sent to the same partition, right? If there's no partition specified and there's no key, because you can do that, then we're going to use what's called the sticky partitioning strategy. So that says that we're going to take a group of data, and we're going to ship it off to partition 0. Then we're going to take a similarly sized group of data and ship it off to partition 1 and 2 and 3 and so on. And so in this way, we are evenly distributing the data in the case that we don't have a key, right? Because you might want to just, you might not care about the keys of your data. You might just want to process downstream and it doesn't matter. But you still want to make sure that you're avoiding hot partitioning so that no one downstream application is faced with the brunt of that data, all right? So that's the default functionality. We also have the round robin partitioner, which is kind of what it sounds like if you're familiar with round robining. And I do want to call out where things actually are named properly, because there are some things in Kafka that just aren't named properly. So let's celebrate the ones that are good. Round robin partitioning strategy. So for this one, each record in a series of records that we're sending to Kafka, we're going to take the first one and send it off to partition 0. The next record, partition 1, 2, 3, and so on and so forth, and we're going to go back around, right? It might sound like that's going to do exactly the same thing that we saw in the sticky partitioning strategy, right? We're just doling out the records. But there were some nuances in the round-robin partitioner that made it so that, yeah, we still had hot partitions. It wasn't really that great. And so the default functionality is much better in that way. And then if you're feeling wild, you can implement your own partitioning strategy. This is good. I've seen this used really, really well in like financial services where you're using like market data and you have hot partitions based on securities. Everybody is buying Apple today, right? So we want to make sure that we have a custom partitioner implemented so that we don't send too many hot securities to one partition, right? All right, so another important configuration, partitioner ignore keys, exactly what it sounds like. So if true, we're going to ignore keys for the purposes of partitioning, all right? So if you've ever wanted to still have a key as part of your message, but you don't really want any of the messages to end up on the same partition, like it doesn't matter to your processing, right? Then this is going to be helpful because you can still uniformly distribute your messages across all the partitions, but you still get the benefit of being able to use a key later on if you need that. And then others to know, we have the partitioner adaptive partitioning enable. So when this is true, it's pretty cool. It's going to look at the current set of brokers that we're sending data to partitions on those brokers. And it's going to assess how fast those brokers are in responding to storing that data. Okay, so if those brokers are slow for any reason, we are going to try to reduce the amount of messages we're sending to those brokers and send more data to the faster ones that can handle it. And the second one here, partitioner availability timeout, is used in conjunction with that. So if you try to send data to a broker and it takes longer than this timeout, then okay, that's the limit. We're going to stop sending data to that broker for a little bit. Give it a breather. Okay, so we have our raw bytes now. We've determined what partition this message should go to. And cool, we could send it off to Kafka right now. That would be completely fine. But messages aren't always sent individually, right? Yeah?
I'm sorry.
Yeah.
Before you go further past, what is a partition?
What is a partition? So the Kafka topic is the data set, like the general data set that we're trying to store that data into. So basically the database table, right? So we have that row in there. But we want to be able to split that up and basically shard it across machines because Kafka is a distributed system. So the partitions are the way, the logical unit that we break it down into so that we can store it across the nodes in the cluster. Cool. All right, so it's not always efficient to send records individually. Okay, so it can be better for throughput, better for latency if we group messages together based on their destination partition, what machine we're trying to send them to, and then send a chunk of records at the same time. There's a lot of really important configurations that have to do with this idea of batching. And I'm going to tell you right now that if you're having any issues with data not being stored in Kafka properly or you're having issues, it's probably because of batching. So this is pretty important because there's a dance. There's a lot of nuances here. But the first thing that you'd want to control when you're trying to batch your data is, okay, how big of a batch should we limit it to, right? The batch size. And then keep in mind that as you're building up a batch, the records in a single batch are going to be destined for a single partition, okay, for a single broker. Okay? So keep that in mind when you're actually configuring this. The default is 16 kilobytes. And there's a couple important things to note. So if your records are larger than batch size, you're not batching. Okay, we're going to send one at a time. So you should probably, I don't know what your data looks like. That's important. That's like step 0, all the way in the back. If batch size is set to 0, then batching is disabled. Okay, we're not batching. If your batch size parameter is set to something relatively small, then you're going to be sending more frequent sets of smaller batches off to the broker. This means that throughput will probably go down since we're adding more round trip time to with those requests every time you're trying to send it to the broker with fewer events. On the other hand, if we set batch size to something larger, you could potentially increase throughput, but then we also run the risk of other things like, wastefully using memory on the producer client. Okay, so there's some trade-offs here. And keep in mind that when you're dealing with batch size, this is just one upper bound. there is another lever that we control, a time-based component, and that is linger MS. So these two things are used in conjunction. So linger MS is how long we are going to wait to try to fill up a batch. Okay? Linger MS is going to be set to 0 by default. So even if you're playing around with batch size and you forget about linger MS, well, okay, we're not building up a batch. All right, it's not going to work. If you want to batch your data for better throughput and you're playing around with linger MS, know that you're doing it at the expense of potentially adding that much latency to every request, right? Because whatever you choose for that, that's going to be the upper bound that we're waiting before we send off a request. That said, playing around with linger MS could actually improve latency by reducing pressure on the brokers. So it's something that you have to figure out based on your data set and what actually works for your clients. So again, batch size and linger MS, they go hand in hand. Whenever we're batching data, we're going to wait for one of these thresholds to be hit. Either we hit the size threshold and we want to ship off that batch, or we've waited long enough and we want to just take what records we have and ship it off to the broker. And then there's some final overlooked, if that wasn't bad enough, there's some overlooked configuration, buffer memory. So you could get everything more or less right with batch size and linger MS, but you could forget about buffer memory and then, okay, and this is the most commonly forgotten one. So while we're waiting to batch our records, we have to store them somewhere, right? And it's gonna be on the producer client. Cool. So this buffer memory is how much space we're allocating to store those records on the producer. By default, it's about 32 megabytes. But the producer also uses additional memory as well. So especially if you're like containerizing any of your applications, oh my gosh, you gotta know what you're doing here. Make sure you have enough memory allocated. So obviously, buffer memory should be larger than batch size, or you're gonna hit some problems. Like that's not cool. You're gonna lose some data. And another thing to note is that for most producer clients, when the producer client starts up, it'll see this configuration, and it's going to allocate that chunk of buffer memory, right? And then it's going to look at your batch size configuration, and it's going to split up that buffer memory chunk of space into chunks of size batch.size. So it's already sort of pre-allocated how many batches you can be dealing with at the same time, and how many that you can build up in tandem to ship off to the broker. Okay, so that's it. That's pretty much batching. There's some other smaller ones in there, but these are the main ones that you have to pay attention to if you want to try to get this right. So there's a lot of good that you can do with batching. Like I've seen a lot of people do really, really well and improve their latency and their throughput by tweaking these a bit. But there's a lot of bad that you can do with it. So how do you know if you're doing it right? Well, metrics, right? We got to find the right balance here. And so the most obvious thing you'd want to keep track of when you're trying to get batching right is the size of the batches, right? Just a good sanity check. Check on how large these batches actually are that you're shipping off to the broker. You'll want batch size average to be as close to batch size as possible, whatever you're setting that parameter to. If batch size average is consistently lower than batch size, then it could be that linger MS is not high enough, right? You're not actually waiting long enough to build up a batch. On the other side of things, if your batch size is low and linger MS is actually pretty high, then okay, you don't actually need linger MS to be set that high. Your client isn't trying to produce records that quickly, and you're adding unnecessary latency there. Next, we have records per request average. Most of these are exactly what they sound like, so that's good. we did well on these. So average number of records per request. Again, if you want to batch, this is a good sanity check just to make sure that things are going as expected. We also have record size average. Yeah, just to help you monitor for tuning. Again, just a good sort of sanity check here. Because again, if this is getting close to batch size or if it's above batch size, then okay, you're not batching. You know right away. Then we have buffer available bytes. So this is going to help you keep tabs on how much memory the producer client is actually using and how much is filled as it's waiting to batch. And this is kind of important because the producer, in most cases, is going to hold on to the data that's in that chunk, that batch.sized chunk of memory and buffer memory until it receives an acknowledgement from the broker saying that that data has been stored. Okay, so it's going to hold on. So this is a good thing to check to see how much memory you have left to use. And then we've got record queue time average. And this word queue came out of nowhere because I haven't talked about it yet, and it kind of seems a little weird. So as we're building up the batch, we're effectively adding these records to a queue in buffer memory, right? So record queue time average is how long those records are actually hanging out while you're building up that batch. So again, sort of a good sanity check. And it's a good way to keep tabs on how long you're lingering on average before sending off that batch. Okay, we have our raw bytes. We know our partition. We've probably batched. Yeah?
So did you say batching is done by partition?
Yeah, so when you build up a batch, it's going to be shipped off to one partition.
Does that mean the producer is responsible for choosing the partition?
Yeah. So the partitioning strategy, that's something that the producer is going to handle. So yeah, all of this is on the producer client, completely independent of the broker. Broker doesn't care. It just wants to know where it should store it. Yeah. All right, so we've batched. An optional stage here is that we could take that chunk of batch data and we can compress it further. This is useful because there are limits on how much data the broker can actually receive at once in some cases. So that is configurable, but in a lot of times, as we get into some of these configurations on the broker itself, if you are not managing, like you individually, if you're not managing your Kafka cluster, the person who is doesn't want you to change these. Or they want a really, really good reason before they tweak some of these. But again, it is good to know them just in case. But for compression, this is disabled by default, but you can change it with the compression.type parameter. And there's a couple available out of the box if you want to play around with it. Finally, OK. We have our raw bytes, we partitioned, we batched, maybe we compressed, and now we can take those cute little batches, all right? And remember, every batch is going to be destined for a single partition, and that partition lives on one broker somewhere. And so now we can take all of the data that is destined for a single broker and ship it off to that broker. Make a request to that individual node to store this data, okay? So, and then again, so we could have multiple batches destined for a single broker at this point. That's possible. There could be multiple. It might be the case that, hey, or in a very silly way, maybe you have all of your partitions on one broker. You shouldn't do that. You should not. But yeah, that could be the case. And so this is, we're going to kick off the first actual stage of leaving the producer at this point. So how does this happen? Well, every producer is going to maintain some socket connections with some number of Kafka brokers based on where these partitions live. And on startup, the producer is going to receive that metadata from the Kafka cluster. So it knows where each partition for this particular topic lives in the cluster. Okay? It has that metadata. It's ready to go. And so they're going to send requests using binary protocol over TCP. So it's request response. We are asking very, very nicely that the broker, here's my request, please store this. And the broker is hopefully going to respond nicely and say, yeah, we've stored it. Cool. And we're mostly just like shipping it off at this point. It's asynchronous. But the producer, you can configure it to be more of a synchronous process if you want to wait and make sure that the data is received. OK. Now, before we get onto the broker, yeah?
Are you using broker and nodes interchangeably?
Yeah, I am. Yeah, the brokers are the nodes in the Kafka cluster. Yeah, sorry about that. So now we're kicking off the first phase of the journey. We can get onto the broker. But before we do that, there's a couple more configurations that are directly related to things on the producer side. So I just want to make sure that we cover them. So first up, max request size. All right, the default's 1 megabyte. This is going to directly limit how many batches we can ship off at once in a single request. Okay? And again, the brokers have a limit on how much data they can receive. So hopefully this is less than whatever limit they have set. Next, this one's really important. How many of you have heard of ACKs in Kafka? OK, hopefully everybody. You're going to learn about it now because this is super important. And this is going to control a lot of the process moving forward when we get onto the broker. So for high availability and fault tolerance in Kafka, you can optionally configure your topics, the individual partitions, to have copies across the cluster. So when you have those replicas set up, when you produce data to a partition, we're first going to go to the lead copy, the golden copy of that partition, store the data on that broker, and then the other copies, the followers, are going to request to store that data in their own time, right? So that we have additional copies elsewhere that are up to date. So without going into too many additional details, because this could be 3 talks on its own, ACTS effectively answers the question, how many replicas should we confirm that this data is written to before we tell the producer we're done? This is good. And that is a gross oversimplification, again, multiple talks on this, but generally that's pretty much what it does. The default is all of them, right? I would like all of the copies to have an up-to-date copy before I move on with my life. But you can throw caution to the wind. You can set this to 0, cool, or 1. Just make sure it's stored on the lead broker. Once the requests are actually sent, max in-flight requests per connection is going to come into play. Remember, producers are maintaining connections to as many brokers as they need to based on where the metadata from the cluster says that these partitions live, right? But we don't want to inundate any one broker with too many requests, right? And so this puts a limit on the number of requests that we could have issued to a single broker at any given time. Another important duo of configs here are enable idempotence and transactional ID. So the default functionality in Kafka now is that idempotence is enabled, which is good. We like idempotence. That's fantastic. So with that enabled, we are enforcing all of the defaults that we just saw. We're enforcing that the max in-flights requests per connection is 5. We are setting ACTS equal to all, and we're also allowing retries to be enabled, right? So if something goes wrong, if this data isn't actually stored, we're gonna let the producer client try again, okay? So idempotence is great. Within a producer session, we can ensure idempotence of the messages that we're sending to Kafka. I like that. That's a good thing. If that producer goes down for any reason and comes back up, idempotence can be broken, okay? So if you want to maintain that sort of functionality across producer sessions, you need to start using transactions. Okay, and you do that by setting a transactional ID. There's a huge asterisk here, and that is that setting the transactional ID does not mean that you're doing transactions. You do have to start the transaction, commit the data, and so on and so forth. There's extra steps you have to do in your producer client to make transactions happen, but this is how you start. You set the transactional ID, okay? And so when you start using transactions, then you have idempotence across your producer sessions, which is good. I like that. That's a nice thing. Okay. And then we've got request timeout MS. Once a request is actually sent off to the broker, this is the maximum amount of time that the producer is going to wait before optionally retrying or throwing an exception. Retries themselves are configured by a couple other configurations here, and know that retries are set to infinite by default. We're going to keep trying. Okay. And again, as we get further into this talk, deep into the depths of the broker, most of these metrics are going to be related to the request and the response that we're sending back. But I do want to highlight a couple that are directly applicable to the configs we just saw. First is request rate. So this generally is going to describe the number of requests that are being made per second by that producer. Then we have requests in flight, again, to sort of keep tabs on the number of requests that are currently in flight for a given broker from that producer. And this is a good thing to check and keep tabs on just to see how bogged down your brokers are generally, and seeing if your producer is making an appropriate, for whatever appropriate means for you, number of requests. Ideally, you want this to be pretty low to show that the brokers are healthy, right? And then we've got request latency average. Once the requests are actually issued to the broker, we're going to start a timer. And so that timer is not going to stop until the producer receives a response for that request. And this is going to describe the amount of time it takes to happen. I did miss one thing. I just remembered now, and I want to go back real quick. Does anything seem suspicious on this page?
Well, don't you have a bunch of things that are eventually in conflict with each other? I mean, you got the requests that are out there, you got the acts that are out there, and then you've got the transaction IDs all at once. At some point, do we run out of concordance with each other?
No, because they're all going to be sent at once. And I'll just get to that on the next slide, actually. But that is a good question. But I will reassure you, that's not necessarily an issue. The thing that I don't like here is the number 5. Doesn't that number 5 seem a little suspicious? Like, why 5? To maintain idempotence within a producer session, we can have up to 5 requests from a given producer, it seems very absurd to me. And I have asked many people about this, including the current PMC chair of the Apache Kafka project. And he assured me that 6 didn't work. And so we have 5. I just wanted to share that tidbit. So anyway, so 7 was insane. Don't even get me started. Yeah. So here, before we actually leave the producer, I know we will at some point, I just want to highlight what this produce request actually looks like, because there's a couple nested things here, and it's good to visualize, I think. So we have the request itself, which is bound by the max request size that we've configured. And then we have some important metadata that we want to keep track of when we actually issue these requests. So the transactional ID, that's really important, so that we can keep track of, even across those producer sessions, right, maintained idempotence. Axe is actually on a producer basis, right, whatever that client actually needs, so that's sent as part of this request as well. And then we have the timeout that this producer is adhering to. And then we actually have the payload of data that we're trying to store on the individual broker. And remember, this request is just destined for one broker. Right? So all of this data is going to be stored on that one. And so we could have, you see the batches there, but we could have multiple batches for a given partition for a given topic. That's possible. We could have multiple partitions for a given topic. We could have data for multiple topics as part of a single request. I personally don't really write producers that write to multiple topics, but you could totally do it, and that's completely fine. So this is sort of like a worst case scenario of all the different things we could toss into one request at the same time. But again, it's all destined for one broker. All right, we're done with this part. So 3 hours, you wanted 3 hours of content? No, it all goes pretty fast here, because remember, this takes like a couple milliseconds, right? All right, so the producer, we finally formulated this request, and we can toss it off to the broker, okay? We're going to throw it out into the ether, and hopefully something good happens. So to get back to the analogy here, our story, our hero has left his cozy hobbit hole. We've packed our bags. We're going straight in the Middle Earth. It's going to be great. All right. This was arguably the most difficult part to make work. And a lot of those configurations, the batching ones, that's very importantly going to happen on the producer, and that's good because you have control of it if you are just using Kafka as a black box, right? That's a good thing. I want to be able to pull those levers. So now we've sent our request out into the ether. What's the first thing? First stage is that we're going to end up on the socket receive buffer. All right, this is sort of a landing zone for all of the incoming requests. And here, the request is going to await being picked up by a network thread for processing. There are some low-level configurations that you can tweak at this point, but again, if you are not managing that cluster, don't just go in and and change it, please. So you might want to control the size of the buffer and also the max bytes that you can receive for a single request incoming. From there, after a very, very short stay, we're going to be picked up by some available network thread from the network pool. An important thing to note here is that whatever network thread picks up this request, it's going to follow it for its whole lifetime within the broker, okay, until we send a response back. The first job of the network thread is to just read that request from the socket buffer and form it into a produce request object, because the broker isn't just handling storing data, it's also handling requests to serve up data. Okay? There's a number of other requests that it's being inundated with. Your produce request is not special. Okay? So what we're going to do is we're going to pick it up and make sure that it's formulated into a request object. And then we're going to add it to the request queue. Again, there's some advanced configurations that you can tweak at this point. Generally, you won't have to change them, but they're good to know. Just in case something goes catastrophically wrong, you can change it. So the first up, we have the num network threads. This just defines how many network threads that we have available in the pool. The default is 3, and the upper bound is typically going to be the number of cores available on your server. A good way to monitor how well these threads are performing is using network processor average idle %. We're getting into the really annoyingly long metrics here because they're all in the broker. And we like to smush them together. We got rid of hyphens for some reason. I don't know why. So the values range from 0, meaning that the threads are fully utilized. We don't like that, to 1, meaning that the threads are not very busy. We like that. We want to be closer to 1. And so after, this is another short stint for our hero. I'm still trying to make this narrative work, right? The requests are going to be added to the request queue to await further processing by the server IO threads, okay? And they're going to be the MVPs of this story. So you have control over this request queue, the maximum size of the request queue, and also the max requests that can actually sit on this queue as well. A general rule of thumb is to set queued max requests. If you're gonna change this, you want the upper bound to be the number of active clients that you potentially have. And so by doing so, this means that you can ensure strict ordering of your messages within a partition. And that's a good thing that Kafka does pretty well, so you might want to do that. Okay, so you can monitor the request queue, as well as the amount of time that a request sits in the request queue. And these metrics together are a pretty good proxy for how long your IO threads are taking generally, and if your broker is overwhelmed. And this is really important because if the request queue is full for any reason, we're gonna block. And then you're gonna get those mysterious cryptic error messages on your producer, and we don't like that. So next up, IO threads. They are, again, doing the heavy lifting, the bulk of what happens next, bless you, is gonna be handled by the IO threads. And this is where we're actually gonna write the data to our broker, so we're almost there. The IO threads are also known as the request handler threads, which makes sense. They're handling the requests. We like that, but I don't know why it's in the documentation as IO thread as well, when all the metrics are named request handler threads. So I tried. Someone issue a pull request. All right, so when the thread accesses this request, the first thing it's gonna do, because we've been shipping around a lot of raw bytes, we wanna make sure that that data hasn't been compromised accidentally, right? So we're going to do a cyclic redundancy check just to make sure that the data that we got is still the data that we wanna store. And again, the IO threads are gonna be doing a lot of work here, so you might wanna configure how many of them there are. You can change the number with num IO threads. The default is 8. If you wanna monitor how these threads are doing, we're gonna use request handler average idle %. Again, you ideally want this to be as close to 1 as possible, showing that the threads are idle more often than not. A value closer to 0 means that they're working overtime. And finally, what we've been waiting for. We're deep into I don't even know, I can't keep this up. We're gonna write this data to the disk, okay? So again, IO threads doing the MVP here. And so if you're familiar with the storage the format of storage in Kafka, it's a log, a commit log. And so on disk, the commit log consists of a collection of components called segments, and each segment is built up of a number of files. So the first, most important one is the actual log file itself. We're going to store the data that the raw bytes that we're trying to store, those events. The second is an index file. We have two index files we're gonna deal with, but the first one is going to map a record offset, which is a monotonically increasing number that identifies that record and its position in the overall partition. And we're gonna map that offset to its corresponding location in the actual log file. The other index we have is a time-based index, because you might want to be able to seek by time and access a record by time in that partition. This is used especially for consumers in disaster recovery scenarios. And then finally, we've got a snapshot file. This is going to store the producer sequence numbers, which are used for when we have idempotent producers. And then, so when the IO threads are actually writing to these files, right? IO is expensive, right? Writing to disk is pretty expensive, and so I know I promised you that we were going to disk, but how about page cache? Let's meet in the middle. That sounds pretty good, right? That might sound a little worrisome, right? We're writing to page cache, but what if everything burns down, and then where's my data? I don't know. I'm gonna say it's good enough. But also you can configure it to effectively flush that from page cache to disk. You have control over that. You can also tweak how often these files are rolled, the individual segment files, the flushing to disk, how often we write to the different index files as well. And yeah, so if you want to change these, or if you want your Kafka administrator to change them, maybe check into the docs a little bit. But you have a lot of flexibility on this. And additionally, a lot of these can be overridden at the topic level. The most common one is the cleanup policy. We saw that, if you remember, all the way back when we set up that topic. We enabled a specific cleanup policy, which was delete. This can take 2 values, either delete or compact. So delete means that old log entries, and old can be defined by a size-based limit, like how much data are we storing in that topic, or a time-based limit as well. And so anything that's over that size or time-based limit, we are going to try to clean it up. We're going to delete it. Cleanup policy compact means that we are always going to do our best and store at least 1 value per key. Okay, so it's going through and it's compacting old messages and just keeping the most recent value. Okay, so the best way to monitor things at this point, specifically how often your log is flushing to disk, you're going to use log flush rate and time ms. It's also important to note, another interesting metric here is local time ms. So local time ms is the amount of time that this IO thread on this broker spends trying to store that data on this local machine. Okay, as soon as it gets that information, that request, and when it leaves it in page cache, it's done. Okay. Okay, we've made it to disk asterisk page cache, which is pretty good. So quick aside here, because there are a bunch of other scary arrows over there for tiered storage. How many of you have heard of tiered storage? Okay, it's because storage is pretty expensive, so we want to offload it to cheaper storage. That sounds great. So the IO threads are going to handle that as well, if need be, okay? There's different implementations of this out there, so I'm not going to go into these details, but just know that, yeah, the IO threads are going to handle it. Okay, so once the data is written, the IO threads they've done the IO. They're free to go on their merry way, which is good because they have a lot of data to store, right? But there should be a huge red flag here. What is the red flag? The red flag is that we've only stored this on 1 replica. And if I had ax equals all, okay, who's storing the rest of the data elsewhere across the cluster? It might surprise you to know that it's not, this broker doesn't care. It's moved on. These IO threads have done their job. They've stored this data on their machine. And that doesn't mean that we're going to go back to the producer and say we're done yet, because we're not. We haven't received the full acknowledgement from the other replicas. But it's up to the other replicas to handle this, all right? And so the IO threads on this machine, they want to move on. So they're going to drop off this request in purgatory. That's it. That's what we decided to call it. It's purgatory. And we're going to leave that request there until it's fully fulfilled by the rest of the brokers, and we reach that ax, okay? So purgatory, what is it? It's a map-like data structure based on a hierarchical timing wheel. There are fun papers out there on it if you want to read it. But you don't have to. So the requests are just going to hang out here for a bit, yeah, again, until we reach the acknowledgements before the other brokers with the follower replicas request that this data is stored on them, okay? So that's going to be sort of a set of meta requests, right? That those brokers are going to make a fetch request to this broker. It's a different type of request. It's not the same one that you would make as a consumer. It is specifically reaching out for data to be replicated, okay? And so that whole thing is going to go through the process. They're going to get their data, send a response back to those brokers, and once we're good, then we can pack this request up and start sending it back as a response, okay? So replication. You can set the replication factor across the entire cluster, like have a default be 3, which is probably a good idea. We'd like to replicate our data just to be safe. You can also set it per topic if you want. So the data replication process, like I said, is triggered by the other brokers that own the copies of those data, and they want to stay as in sync as possible. How do they actually do this? Well, we have what are called replica fetchers on those brokers. These are additional threads that are solely out there to make sure that their copies are up to date. So you can set this to some number. I think the default is 3 as well. Maybe it's more than that. Well, 5 is already taken, so that's silly. What a ridiculous question. And then we have replica fetch weight max ms. So We obviously don't want this, this replication process to take too long. So replica fetch wait max ms is the maximum amount of time that we can guarantee between that the data will wait before it's replicated. Okay? It's set to 500 milliseconds, which sounds like a lot. You can change it, although I am currently talking to someone who's running individual performance tests on this, and he said it only takes 6 milliseconds. And that sounds great. I love that. That's even better. So it's pretty efficient at this. OK. So for monitoring, remote time MS. So local time MS was the amount of time it took to store the data on the local machine. Remote time MS is the total amount of time it takes once we drop off this request in purgatory and when we finally fulfill our acknowledgements for that request. Okay? The remote brokers have done their thing. Okay? Okay. Then we can start to form a response object to send back to the broker because, okay, hooray, the data has been stored on this machine. It's also been stored elsewhere, or our acknowledgements have been fulfilled, so we can move on. We will then put that response back onto a response queue. Same process, but in reverse, right? You can't really configure the response queue like you can the request queue, but we can monitor it with similar metrics, the size of it, and the amount of time that the response sits on there. Okay. We also have something. We have response queue time MS. So we had local time MS. We had remote time MS. You'd think that if you looked at a whole timeline of a request and a response going through this process, that we just add them all up. And right, we have this nice chunk of time that describes the whole thing. That's not the case. And so response queue time MS is not factored into the total time. So I will remind you later. It's a weird nuance. I'm still, again, trying to track down why. It's a learning process here, folks. OK, so back to the network threads. But really, they were with us all along. Isn't that heartwarming? Right? Because that network thread that picked up the initial request has been handling this whole process the entire time. And so now we're sort of, its last task here is to just basically kick the response back on the socket send queue, the send buffer. OK, so we're going to send it, put it on the socket send buffer to await being picked up by the producer. And the broker is going to wait until the entire response is picked up by the producer before we move on. And again, we have some low-level configurations here, the size of the send buffer. And then we have response send time MS, the amount of time that actually takes for that response to be received by that producer at this point. OK. So at this point, if all of our acts have been fulfilled and we didn't hit any weird little snags, we've received a good response. And so we can clear out whatever that batch sized chunk of memory in buffer memory, and we can start moving on and building up a new batch as well. Okay. I want to summarize these time metrics again for that lovely little timeline of things that don't add up. So for total time MS, the amount of time that this entire process takes, it is comprised of request queue time MS, the amount of time we spend on the request queue, our local time MS for the I/O thread actually storing the data on the local machine, our remote time MS for how long those fetchers actually take, and then our response send time MS. And all the way at the bottom there, response queue time MS, we're not going to add that in there for some reason. So if you are looking at all these metrics and adding them up and you're upset, don't be upset. It's just, it's a feature. We like it. OK. And so just as a summary, because I know this is exhausting and there was a lot of information here, but we covered a lot of ground, right? And so I know that I completely just inundated you with a bunch of configurations and a bunch of metrics, but I did select them solely for you. They're all really important configurations, and even if you are not tweaking them, I think they're good to know, because the thing I hate most about software engineering is you don't know what you don't know. And if you don't even know where to Google, or if you're looking at the 3,000 configurations that you can tweak for Apache Kafka, it's really hard to know where to look. Okay, so here are some of the most important ones that I thought you should be aware of the next time something goes wrong on the producer side, so that you can hopefully have a little more, a more useful debugging session. All right, and I hope that this is more encouraging than overwhelming. But if you want to be overwhelmed, I'm currently writing a talk on the consumer side of things. So yeah, maybe next time I'll do this one. But yeah, we're going to follow pretty much the same process whenever you are requesting data from the broker as well. We're going to go through all the same stages to build up a response with a chunk of data. So Yeah, I mean, honestly, just to summarize, I think it's incredible that Kafka works and it works quickly. It's a really, like, I don't want to say that in like a bad way, like wow, it's amazing, it works. No, it's a really sophisticated piece of technology and it does so much for you, so much heavy lifting behind the scenes. And so yeah, the next time something goes wrong, like don't get too frustrated, just hopefully one of the metrics we covered today will help you out. And so we can just marvel at the black box again. So yeah, don't be discouraged. You should. I know a lot of you said that you've heard of Kafka. Maybe you're using it. If you're not using it, please try it out. It's not as scary as some people say. It's actually really fun. I don't like that face you just made. It's a fantastic technology. So I encourage you to play around with it more. So this is my link tree. On here, I will cycle out some interesting resources that I found recently, articles, fun projects that I'm working on. But the most important link on there is a link to Confluent Developer, which is our developer portal. So I am a developer advocate. I work on a team of tirelessly of engineers and developer advocates that we are constantly building out resources to help people who just want to understand Kafka better. So if you are new at Kafka, we've got introductory free courses on there to help you get started. There's courses to go even deeper than this into internals if you're curious to know more. So yeah, there's a lot of good stuff on there. And so I will leave this up now so that you all can use it if you want, but I can take questions now. So I appreciate it.